Hi everyone. In this video, I will try to explain what is solidification crack, what are the reasons for the formation of solidification crack in any weld, and what are the steps we can take to prevent them from occurring. Okay. So in the last video related to the type of defects in weld, we have seen that first important defect is crack. So in crack, we have seen two categories, rather three categories. One is hot crack, cold crack, and then we have seen lamellar tearing. The solidification crack, which we are going to discuss, comes under the category of hard crack. So in the last video itself, we have understood hard crack is nothing but a crack which occurs in the weld at an elevated temperature. At an elevated temperature. So basically, elevated temperature here means that it will get formed at the time of completion of solidification. So at that time only we will see this solidification crack getting formed in the weld. Okay, so I have taken some images from the book available in Welding Metallurgy and Weldability by John C. Lippold. So these are the two images I have taken. You can see how solidification crack occurs with respect to this second one is this one is aluminum based alloy, and this one was seen in nickel based alloy, that is IN Inconel 718. So you can see how the solidification crack occurs or looks through the microstructure. So solidification crack generally occurs in center of the weld mostly. So we know that in any weld we have three important zones. One is fusion zone, where the material will be heated to melting point. Adjacent to that, we will be having a heat affected zone. So this is the heat affected zone. So mostly this solidification crack can be seen at the weld center. So if you see any crack in the microstructure at the weld center, you can confirm that this may be due to it may be one solidification crack. Okay, so that is one important thing you should note on where it occurs, mostly at the center of the weld. Okay, so what is the reason for the formation of solidification crack? If you see, it is mainly due to the presence of low melting alloy elements. Okay, so we know that in any material we have some impurities like sulfur, phosphorus, whose melting point is comparatively lesser than the main elements. So what happens because of this presence of low melting alloy elements during solidification? I'll again try to explain with the help of a diagram. So I'll just show. So this is the interface, weld interface, and here we have this heat affected zone. This is the heat affected zone. So this area generally material will be heated above the melting point. So during solidification, what happens is that grains will be growing from the interface towards the weld center from both the ends like this. Okay, so during this time, what happens is that this low melting alloying elements such as sulfur, phosphorus will be pushed towards the center. So it will be pushed towards the center, since its melting point is low. The surrounding area will be completely solidified. These areas would be solidified after a certain time, whereas the low melting alloying elements will still will remain in liquid form. This is the liquid form, let us assume. So these area will be fully in a solid state, as they have higher melting point. This low alloying elements melting point is lower, so it will be still remaining in liquid form only. So what happens is that this solidified part acts upon this liquid film, giving us stress, and it will result in separation of this liquid film. Separation of liquid film. So this separation of liquid film leads to the formation of crack. Okay, so let me again repeat. So during solidification, and the grains will grow from the interface towards the center, and the low lying elements such as sulfur, phosphorus will be pushed towards the center. Since its melting point is low, other areas would be completely solidified. They will be in solid state. This low lying element will still be in a liquid state. Since other elements are in solid state, this will act upon this liquid film, resulting in separation of that liquid film, leading to the formation of the crack. So this is the main reason for the formation of solidification crack in the weld. That's why I have told you the location of the solidification crack mostly will be at the center of the weld. Okay. So next we'll see what are the factors that will control that will result in solidification crack in any material. Okay, so first foremost thing is chemical composition. Let me explain one by one. First important point is chemical composition. So that in that because of wider solidification range, we will give it will result in solidification crack. For example, we know that how pure metals will solidify. I'll show a simple example. So this will be the time in the x-axis and temperature in the y-axis. So pure metal will solidify at a single point, single location, single temperature. At this point it will start to form liquid particles, solid, and at this point solid will be completed, solid formation will be completed. So you can see the solidification is taking place at a single temperature. This is with respect to pure metal. Whereas in case of alloys, the solidification behavior will be over a wide temperature range. Okay, so this is the major reason for the formation of solidification crack. Okay, so at this location solid particles will start to form. At this location it will be completed. So you can see there is a temperature gap, temperature difference. Let us say it may start at 1000 degrees Celsius and end at 900 degrees Celsius. So it has a solidification temperature of 100 degrees Celsius. Okay, whereas here it starts at the same temperature, ends at the same temperature. Since it is having wider solidification temperature range, it will be resulting in formation of solidification crack. So this is one of the important problem with respect to alloys. So we have a lot of alloys since it results in better mechanical and corrosion properties, but when we are trying to weld that alloy, it will result in the formation of solidification crack because of their wider solidification temperature range. Okay, next we will see some examples how the solidification temperature range affects. This was again taken from the textbook Welding Metallurgy and Weldability, published by John C. Leopold, okay, Willy publication. So you can see in this picture, x-axis they have taken solidification temperature range, and y-axis they have taken crack length. As you can see, with lesser solidification temperature range, that is less than 100, you can see in this area the crack length is less than 1 mm. Whereas when the solidification temperature is in this range, that is between 125 to 225, this region, you can see the crack length is more than 1 mm. In some cases it is around 1.5 mm, 1.7 mm, something like that. Okay, so this black color is related to nickel based alloys data, and this simple unfilled square box corresponds to iron based alloys. Okay, so based upon the previous understanding, the same thing can be seen in this graph also. With wider solidification temperature range, the crack length is also getting increased. Okay, next we'll see a formula which gives which gives an idea about whether the cracks will occur or not. For example, with respect to alloy, 230C plus 190S plus 75P plus 45 Nb, 12.3 silicon minus 5.4 manganese minus 1. Okay, so if this value CS value is less than 20, it will have better resistance to solidification crack. Since we have seen that with respect to alloy, the solidification temperature range will be higher. So based upon the amount of alloying elements, that is carbon, sulfur, phosphorus, niobium, silicon, manganese, they have derived a relation. So if the value is less than 20, generally the resistance for the formation of the crack will be higher. Okay, and another aspect with respect to chemical composition is that generally presence of manganese with respect to any material it will help us to minimize the formation of crack, since it reacts readily with sulfur to form manganese sulfide. Okay, so that's what shown in this graph. Also you can see they have taken carbon content in the x-axis and ratio of manganese to sulfur. Okay, so when the ratio of manganese to sulfur is higher, okay, you can see that the crack formation is very less. Okay, at the same time, when the ratio of manganese to sulfur is very less and carbon content is high, the crack formation is the possibility for the crack formation is more. Okay, so chemical composition plays an important role, since these alloying impurity elements such as sulfur and phosphorus will be existing in a liquid film at the end of the solidification, which is the main cause for the formation of solidification temperature. Okay, so this is what they have mentioned in with respect to this picture, that is the ratio of manganese to sulfur as well as carbon content. So higher the carbon content, more will be the more will be the possibility for the formation of crack. Okay, so next with respect to this stainless steels, alloy based steels, they have found a relation with respect to the percentage of phosphorus and sulfur and chromium and nickel equivalent. So generally based upon the chromium equivalent and nickel equivalent, they will predict what type of solidification it will be, whether it will be solidifying in the form of austenite, or it is ferrite or ferrite austenite. So we can predict the mode of solidification in stainless steels based upon the nickel and chromium equivalent. The formula for chromium nickel equivalent is given in this picture itself, you can see. Okay, so they have found out through research data that if chromium equivalent, the ratio of chromium equivalent and nickel equivalent is higher, okay, if it is higher, the possibility for the crack is less. Okay, so even though there is certain volume of phosphorus and sulfur in the material, if the chromium and nickel equivalent is higher, ratio of chromium and nickel equivalent is higher, the possibility for the formation of crack is generally lesser. That is what it is shown in this picture. You can see in the x-axis they have taken ratio of chromium to nickel equivalent, and the y-axis they have taken volume percentage of this weight percentage of phosphorus and sulfur. Okay, so after crossing 1.5 this ratio, you can see that this unfilled bubbles means that is it is susceptible, not susceptible, black color circle is susceptible. After 1.5 you can see most of the bubbles are unfilled, that means there is no possibility of cracking, irrespective of what is the percentage of phosphorus and sulfur. If the chromium nickel equivalent is more than 1.5, there is a less possibility for the formation of solidification crack, and if you see below 1.5, the possibility for the formation of crack is more, both at a low percentage of phosphorus and sulfur, at a high percentage of phosphorus and sulfur. Okay, this is what they have found through their research work. This this picture is also taken from the same textbook. Okay, so what does that means if the chromium equivalent to nickel equivalent is higher, it will generally result in a ferrite mode of solidification. So generally if a material is having more ferrite content, it will help us to reduce the solidification crack formation, because it absorbs sulfur and phosphorus. It has the capability to absorb sulfur and sulfur. So if you are able to absorb sulfur, then the possibility for the formation of crack is less. So we can, for example, in case of austenitic stainless steel, they will try to maintain a certain amount of ferrite in the weld so that they can prevent the formation of solidification crack. So this is another interesting factor with respect to chemical composition, how the solidification crack occurs based upon the chromium equivalent to nickel equivalent ratio and volume weight percentage of phosphorus and sulfur. Okay, so these are all some of the factors. In addition to that, if based on the grain shape, if the grain shapes are straight, there is a more probability for the formation of crack. Okay, if it is curved means less probability for the crack formation, less probability for a crack. And depending upon the size also, size, if you take a size, finer grains will minimize the crack possibility for the formation of crack. Coarser the grains, generally it will result in crack. That is what it is found in the literature. Okay, so next we'll see some of the steps that we can take to prevent the formation of crack. Steps to prevent crack, that is solidification crack. That is what we are seeing here. First one is you can see it in the diagram in this picture. This is also taken from the same textbook. So whenever the bead shape is in concave mode, you can see it in the left picture, there is a possibility for the crack. You can see the crack is getting formed, and this is also we are having a crack. Okay, if the bead is in the shape of convex, you can see if it is slightly convex, then the possibility for the formation of crack is also less. That is what they have found through the result. So we have to deposit in the form of a convex shape. That will help us to prevent the formation of solidification crack. Okay, next one is if the depth to width ratio, is higher, as it is seen here in the left side, we are observing a crack. If the depth to width ratio is higher, the possibility of solidification crack in any material is higher. You have to maintain it at optimum value so that the crack formation is also prevented. So in this right side, you can see there is no crack since the depth to weight ratio is at optimum value. Generally, at when you are using high power density process such as laser welding or electron beam welding, because of the nature of the process, the depth to weight ratio will be higher. That we have to that will result in the formation of solidification crack. So we have to take extra steps to prevent the formation of crack in those kind of processes. Okay, so it depends upon number of factors, not only on the depth to width ratio or the type of the bead, shape of the bead, and it also depends upon other factors which we have discussed previously. Okay, so we have to make the bead shape in convex. We have to make the bead in convex shape. Then we have to minimize the depth to width ratio. That is, we have to go for optimum value. Okay, and other steps what we can take is that identify correct filler material. Why? Because we seen that in the beginning, the solidification temperature is high, means the possibility for the crack formation is more. So we have to when you are joining any material, we have to choose the correct filler material so that we can minimize the solidification temperature range. That is why extra care should be taken when you are trying to identify them, when you are trying to use any specific filler material for a particular material. Okay, so identify the correct filler, and we have to take all the steps that we generally do to minimize tensile residual stress. So generally we will try to minimize residual stress in any weld. So what are the steps that we are doing to minimize that? The same thing can be applied for minimizing the solidification crack. Okay, for example, we can select the correct groove shape, because it controls the amount of material volume of the material that is getting deposited. More the volume of material, more the chances for solidification crack. So select correct groove shape such that the melting of the material is less, so that, and it can minimize the tensile residual stress. At the same time, minimize the possibility of solidification crack. Okay, and then we can go for preheating. Okay, preheating can help us to minimize the formation of solidification crack. Next one is we can weld in such a way that it results in fine grains, as we have seen in the previous here we have seen, right, the fine grains will reduce the crack length. So weld in such a way that we are able to get fine grains. And in addition to that, we have some more factors like yield strength should be as low as possible. So if the yield strength is a little bit less, then the possibility for the formation of solidification crack is also less, because when we are trying to select the filler material, we should try to select in such a way that the overall yield strength after welding should be as low as possible. So that is another important factor. Okay, so to get fine grains, you can go for grain refinement techniques like using titanium, vanadium, zirconium. All these things we can try to apply to prevent the formation of solidification crack. And then we can take steps in welding to induce the formation of ferrite, because we already seen that ferrite will help us to observe the impurity atoms like sulfur. Okay, so these are all the steps that we can generally take to avoid the formation of solidification crack. To summarize, in this video we have seen what is solidification crack. It is coming under the category of hard crack. So hard crack means it occurs at the elevated temperature. That is what initial definition we have seen. So why it occurs? Because of the presence of low melting point alloy elements, the mainly like sulfur and phosphorus. So during solidification, this will be pushed towards the center. It will remain in liquid film, then surrounding part will be in solid state. It will act upon the liquid film. As a result of that, separation will happen. So as a result of that, will lead to formation of solidification crack. Okay, and the main factors is a composition. So if the solidification temperature range is high, it results in the solidification crack. And we have seen some case studies also based upon the textbook, depending upon the chromium nickel equivalent. If it is higher, we have seen that the possibility for the solidification crack is less, generally because ferrite will be the mode of solidification will be ferrite at a higher ratio of chromium nickel equivalent. So we have to do the weld in such a way that it results in more ferrite in the material. And this we have also seen with respect to manganese sulfur ratio and carbon content, and grain shape also comes into picture, and also grain size and bead shape as well as the depth to width ratio also come into the picture. And finally we have seen what are the steps we can generally take to avoid the solidification crack. Okay, so thanks for watching. See you in the next video.